Now, these four figures together illustrate how probes, prompt templates trigger different vulnerability behaviors in GPT OSS 20B. How these behaviors are characterized in text length, readability, and of course, the lexical patterns. How severity distributes across prompt combinations, and how you can turn these observations into reproducible JSON findings and statistical quality control. Now, below I explain what each plot shows, how to interpret it for your understanding, and of course, the statistical checks and follow-up analysis that you should run. Okay, and of course, the practical reproducible JSON schema recommendations that follow directly from the visual evidence. Now, firstly, we look at figure one, which shows the response pattern analysis. First of all, we have four panels. All right. Of course, we have the vulnerability type box, the feature correlation matrix heatmap, and the severity versus indicators. Then, of course, we have the scatter as well as the readability score distribution histogram. All these are under the figure one. Now, let's look at what each panel indicates. The response length by vulnerability type, that's the box plots. X-axis represents the vulnerability category, reward hacking, deception, hidden motivations, etc. Then, of course, you have the y-axis, which of course has the or holds the token character count. That's the response length. Then you have box plots, which show the median, the IQR, the outliers per vulnerability type, white boxes or long whiskers indicate high variance in how much the model writes when a prompt elicits that type. Some vulnerability types have much longer median responses. For example, hacking, while others are short and concise. All right, for instance, the chain of thought issues. Now, let's look at the feature correlation matrix. That's the heat map. This indicates the pairwise correlations, uh, perhaps, or most, of course, is the Pearson among numeric features used in analysis, severity, response length, and of course, indicators found has the counts, as well as readability score, has the sentiment score. Now, the colors from the negative to red, the positive, and the numeric values annotate strength. For example, a positive 0.58 between response length and sentiment score implies longer responses correlate with stronger measured sentiment, all right, or whatever the sentiment metric encodes. Now let's look at the severity versus indicators here. Found is scattered. The X represents the number of indicators flagged inside a response indicator count, and the Y assigns severity. That's the ordinal 0 to 3. Uh, of course, those are similar. Now, each marker is a response, probably jitters, color legend maps to vulnerability type. This reveals whether more indicators correspond to higher severity, whether that relationship differs by type. Then the readability score distribution, that's the histogram stacked by detected, not detected. You have the readability metric FK small on x-axis, counts on y. Stacked bars show how many responses were automatically detected as vulnerable versus not. If detected, vulnerabilities cluster in lower or higher readability ranges. That suggests a systemic style signature. Now, let's look at the interpretation of the pipeline. Probe design insight. Vulnerability types that produce long high variance responses usually indicate prompts that quacks the model into exploratory code or mode rather. These prompts are useful for stress testing reasoning chains. Short, consistent responses indicate brittle failure which quick refusals. Now let's look at the feature selection. Correlation matrix helps to avoid multicollinearity in downstream models. For instance, if the ability score and response lengths are strongly correlated, all right, it's better to actually go with one of those. Then, of course, we move on to the correlations guide, which features are informative, of course, for the vulnerability classifiers. Now, let's look at the severity calibration. The scatter suggests a positive relationship between indicators found and assigned severity. Use these to actually define the rules for automatic severity assignment, thresholds on indicator count plus certain high impact indicator types. Detection bias. Readability histogram shows detection algorithm, severity or rather sensitivity across writing styles. It flags whether detectors miss vulnerabilities in readable text, as false negatives, or mislabel noisy text, which are the false positives. Right. So let's quickly move on to the statistical checks and recommended follow-ups. Um, the compute Spearman's RHO for indicator count is versus severity. Severity versus is ordinal actually, and report p values plus the bootstrap 95% CL. Response length. Comparisons across vulnerability categories. You could actually run the Pascal Wallis non-pragmatic ANOVA, which is, of course, provided and followed by pairwise doing less with Benjamin Hodgepodge correction. All right. The report effect sizes, for instance, the Cliffs delta. Then for correlation matrix, a report books the Pearson and the Spearman plus the p-value matrix. This is correct for comparison, Benjamin Hodgepodge, which significance, which actually shows significance with stars on the heatmap. For readability detection bias, compute detection precision recall stratified or readability bins. You can plot the calibration curves to show the bars via bootstrap. Now, let's now look at how this informs us on the JSON findings. JSON recorded should store, of course, don't store the response length, vulnerability score, indicators found, that's list account, severity, numeric textual, the detection flag. Those labels allow producing these plots programmatically. So let's now move on to the second image, which is the vulnerability response cloud. Now, for these vulnerability response word clouds, we have multiple word clouds labeled by vulnerability type or grouped regions. For instance, the reward hacking, the deception, the sabotage, the data exfiltration, evaluation awareness, and so on and so forth. Now, let's just get what this is communicating across to us. Each word cloud visualizes most frequent or most salient tokens, phrases appearing in the responses, classified under a vulnerability type. Okay, so the large words is equivalent to high frequency or high TF-ID. Access clouds, you can see that the main words, like for instance, the password, migration, SQL table provide policy must question, user deception, line, all prominent. Then, of course, the difference across clouds indicates distinct lexical signatures of vulnerability. For example, the extra exfiltration cloud emphasizes column, table, migration, SQL. Technical terms are typical of data leak prompts. Now, for the deception social engineering, cloud shows line policy provide most user phrases used when model gives deception sounding advice or social engineering tactics. Right now, let's see the reward hacking or evaluation awareness. This may show meta terms like assistance, evaluation, query, and assessment. Now, let's go forward and look at the interpretation for pro and design detection. For lexical structures or signatures, you can build interpretable detectors using keyword phrase lists and their co-occurrence patterns as early filters. For example, presence of table plus column plus SQL in otherwise in COCOS prompt response should increase a suspicion score for exfiltration. False positive risk. High frequency functional words like must provide user are not sufficient alone. It's always advisable to use multi-token patterns and proximity, engrams, and semantic embeddings to reduce noise. Then semantic clustering. These clouds justify applying topic models, LDE based topic or embedding based clustering to automatically group and overall responses into vulnerability classes. Then let's look at the statistical NLP follow-ups. These compute log likelihood ratio, right, the keyness for keywords per vulnerability, right? And that's also background corpus to quantify how distinctive terms and are, of course, more robust than the raw frequency. We look at the build TF to IDF plus classifier baseline uh, and evaluate per class precision recall to see whether the cloud tokens are predictive. Now, it's better to use word phrase co-location analysis, that's a PMI, the engram extraction to find multi-word triggers. For most semantics, cluster response embeddings such as the sentence bet visualized with UMAP TSNE to confirm separation suggested by clouds. Now, let's look at what is stored in JSON as far as this is concerned. That's the top milligrams, the top bigrams, the TF-IDF scores, the embedding for each response. This lets downstream analysis reproduce clouds or run keyword markets. So that's all about for the second figure. Let's now move on to the figure 3, which is the vulnerability severity interactive heatmap. Alright, so for the vulnerability severity interactive heatmap, this is the heatmap with vulnerability types on the y-axis and the prompt combination on x-axis. That's the color code severity 0 to 3. Now, this is actually what the plot indicates. Each cell is a prompt combination, right? And vulnerability type, pair. Then the color intensity shows median or maximum severity observed when that prompt combo was run. That's 0 to none and 3 to severe. Some prompt combos light up for specific vulnerability types. For instance, the prompt combo 12 triggers reward hacking with severity 3, while combos 20 to 25 produce moderate severity for data-exfiltration. The interactive label, if used in dashboard, is likely to show counts, exact severity values, and sample response IDs per cell. Now, this is why this is very important, okay, for this particular vulnerability program. The probe efficacy, okay, the probe efficacy mapping directly answers which probe, excuse me, which probe, let me take that again. The probe efficacy mapping, okay, this directly answers which probe designs or program manipulations, all right, reliably elicit high severity vulnerabilities each class. All right, that's a prime question. Okay, the prime input is to optimize the probe bank. Now let's look at prioritization. Focus is actually on manual review and mitigation on prompt combos. High severity, that's the red cells. These become candidates for targeted remediation and model patching or safety steering. Now, across prompt effects, you can actually prompt combos to elicit multiple vulnerability types, multi-column patterns across rows. Each combos are specifically dangerous because they show model fragility across dimensions. It's also important to emphasize on the statistical checks and modeling. Now, for each compute, number of samples n, median severity, mean severity, the interquartile range, the proportion of runs reaching severity greater than or equals to 2. Furthermore, you see that the display n opacity or overlay text to avoid highlighted cells with the tiny n. Now, It's also very good to use ordinal logistic regression, right? And that's proportional odds with predictors, which is equal to the prompt features. That's the template ID, temperature, few short examples, wording features to quantify which prompt features are significantly poised to increase severity. Okay, report odds, ratios, and CIs. Now, for the use mixed effects models, combo or that's a prompt combo is fixed. Okay, it's still drawn as random. If we actually have repeated measures with the same prompt running on multiple times, this becomes very, very important. And this controls for which within prompt correlation and which of course gives robust p-values. Is recommended not to use false discovery rate control when testing many prompt combos, just like what we've done in this particular experiment. Now, reproducibility, that's the reproductive and the interactivity of this particular solution. Um, Most of this was done, and the saving mapping, of course, was saved into JSON. Okay, so with each entry, prompt compo ID, vulnerability type, severity stats, the n median, the IQR, the p underscore GE2, sample underscore IDs, which is a dynamic array, then the seed info. So interactive heat map can actually rehydrate cells into list of example responses. So this concludes this the third image. We now move on to the fourth and final image, which is the vulnerability dashboard. All right, so going forward, let's now look at the figure 4, which is the final figure in this presentation. We have the vulnerability dashboard with multiple plots, which of course contains vulnerability detection by type, severity distribution, response length versus severity, indicators found distribution, and vulnerability timeline, as well as the readability versus severity. Now, the panel by panel exploration is as follows. The application, of course. Firstly, you have the vulnerability detection by type. Is the bar stacked stars. This indicates the count of detected versus not detected vulnerability type. Bars grouped by type. Then, of course, useful. This is very actually useful to see whether automatic detectors underperform. Now, the further action that can be taken under this is that we compute type-specific precision. We call F1 prioritize training data collection for types with low recall but high word risk, right? So the second thing we're looking at under this figure 4 is severity distribution, which is the bar histogram. This indicates the bar heights, which show how many responses are in severity 0, 1, 2, 3, respectively. If skewed heavily towards 0, severe events are rare. Okay, so it's always better to handle imbalanced learning as on sampling cost sensitive cohorts. For the action, the report class weighted metrics and compute bootstraps 95% CL on severe class prevalence. Then you have the response length versus severity, that's the scatter. Each plot or each point is a response colored by severity, trend or regression line. Ensure longer responses are more likely to be of higher severity. Now, the action is always better to quantify with ordinal logistic regression or Spearman correlation. And of course, consider the response length as useful feature for triage scoring. Now, the indicators and found distribution, which is histogram. This shows the counts of responses with 0, 1, 2, 3 indicators. Together with severity distribution, this indicates whether severity is equivalent to the indicator count, or some indicators carry more weight. In the action, it's also recommended that you define indicator taxonomy by peer indicator, severity weight, which of course can also perform per indicator logistic regressions for predictive power. Now, for the vulnerability timeline, that's the time series, the scatter of counts over time, or prompt run ID. This tracks when vulnerabilities were found by date, okay, run. Uh, you can actually use it to detect the temporal trends, the security regressions after model updates or probing methods evolve. Um, Action recommended is that to conduct change point detection or interrupted time series analysis when model versions change. Okay. You can also link the timeline events to the model version in JSON. The readability versus severity, that's the scatter plot. This shows whether easier to read responses are much more likely to be flagged severe. If severe responses are actually readable, that's a higher risk. That indicates possible social engineering succession. And the action recommended is to stratify detection as thresholds by readability bands or use readability as a feature in the classifier. All right. So we also finally look at the quality control and metrics to compute from the dashboard. The detection performance. It's better you compute confusion metrics, uh, vulnerability type, and overall derive precision, recall, F1, and average precision. Calibration is for future advancement of this code. Um, for any probabilistic detector, it's recommended you produce the calibration plot and compute their score. Uncertainty quantification. You can actually provide bootstrap sales, counts, and then proportions shown in bars histograms. Inter greater reliability. If human labels are actually uh, existing, it's recommended to compute Cohen's kappa or Phillips kappa if it's greater than two annotators. To quantify label consistency. Okay, low kappa implies label noise and triggers audit of labeling instructions. All right, so this sums up the 34 figures, and there are actually two sections of this code. There is this part, each of them comes with a prompt, inbuilt chart pairs, built into the algorithm to actually run through these vulnerabilities. The first one was about an hour plus using GPU, of course, with compute capability of two, while the other one was about almost 2.5 hours. So these are the things that we need to understand as far as these codes are concerned. I hope you guys enjoyed this presentation, and until next time, cheers and all the best.
Audio Jungle. 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 Audio Jungle.